It's probably why they taste so good. Okay, so here were the fixes on homework 24B and 25B. If you're listening to the lecture for some reason and you weren't here and you didn't remember that we did this, I don't know. Anyway, we needed to finish up reactions. I have no idea where we left off. I'm pretty sure we left off on all the hydrolysis reactions. I'm keeping track, and I think, what? Yeah, with the nitriles. That would be the last of the hydrolysis reactions. Yes, 9 steps that we all ignore and just say, we're all going to make anytime we see a hydrolysis figure, you're going to make a carboxylic acid in something, right? And it's mostly a question of where the molecule breaks apart. Okay, so we also have some substitution reactions. Actually, I guess we normally just do like this. And this is specifically called, well, not specifically, but I mean it's also sometimes called a formation reaction because it's how amines are generally formed. And so it's probably the easiest way to do it. And there's 4 different reactions, 3 of which are identical, and the last one is actually an addition, not a substitution, but it fits in the pattern that we're doing. And so what we're going to do is we're going to realize that we can take ammonia plus an alkyl halide. And what's an alkyl halide really? If we put it in parentheses, it's just any alkane with a halide on it, right? And we can make that into a primary amine plus an acid. And then the idea is that we can just keep taking that. So we can take that primary amine from the first step. We can add a second alkyl halide, and we can turn it into a secondary amine plus an acid. And then, of course, we can take that secondary amine plus an alkyl halide and turn it into, guess what? Tertiary amine plus an acid. And then I'm going to put this 4th step here, but remember that this next step is actually an addition. And it's pretty easy to tell that it can't be a substitution, mostly because there's nothing to substitute off of the amine. And so if I take a tertiary amine and I add one more alkyl halide, then I can get what's called a quaternary ammonium salt. So this is the first series of substitution reactions. And we'll show you all 4 reactions here in a second using some, line drawings, since everyone seems to kind of like that. But I think the key here to remember is that if you see something plus an alkyl halide, just go ahead and do a substitution reaction. Meaning that should be kind of your trigger on this, is seeing that alkyl halide. It's the only reaction, if I remember right, in this section that has an alkyl halide. Yep, looks like it. Okay, you guys good to go on the next one? I guess I'll have to eat a bite of donut. How about, you guys got lots of other tests and classes this week? Pretty clear week, pretty easy week for you. Cool. Okay, so if I take ammonia plus an alkyl halide, then what happens is the chlorine and one of the hydrogens swap places. Actually, I guess technically the chlorine is the alkane group that swaps, but I like to think about the chlorine and the hydrogen going together, so maybe I should draw it like this. So remember, substitutions are swaps. And so I stick that on there in place of a hydrogen, and I make HCl. So I'm swapping a hydrogen and that nitrogen. I mean, the other way to think about it is that you're swapping that chlorine for an NH2 group if you want. And if we draw it out, what we're really saying is that if I've got nitrogen like this, or the ammonia I should say, and the chlorine like this, then what I'm doing is I'm taking that entire alkyl group and I'm swapping it with a hydrogen. Or, if you want to think about it, I'm swapping the chlorine and an NH2 group. Maybe that's even easier to think about it. They both work. That's the whole idea with swaps. Maybe we should also mention that it's a double displacement, so you're used to just swapping things. So if I replace a chlorine with an NH2, that's the exact same reaction. So it doesn't matter sort of which way you think about it. And then the next two steps are simply taking that amine and adding various alkyl groups to it. Meaning this is the exact same mechanism. Here I'm going to swap a chlorine and a hydrogen. And so now I get an NH, and now it's got an ethyl group sticking on it, plus HCl. And then I can take that very same one with an NH and that ethyl group on it, and I can stick maybe, say, just three carbon long alkyl halide. So now I get one with 4, one with 2, and one with 3 carbons on it. And so basically I just keep swapping a hydrogen for an alkane group, and then I get plus HCl. So on a test, you could see any of these first 3 steps. So notice they kind of look different, because as we go down and add more alkyl groups, the starting material kind of looks a little bit more complicated. And so to me, the easiest way to remember this one is that if I've got an ammonia and I've got a alkyl halide, that's a swap or substitution. And then that last step is different, remember? The 4th step is really an addition. And so that's saying that if I've got a tertiary, and we'll just use the tertiary that we had already, like that, plus one more alkane group, and I guess we'll make it 5 carbons since I've used 2, 3, and 4, and 1 can be confusing. Then remember that this is an addition, and so what we're really doing is we're taking that lone pair of electrons and we're making a bond to that alkyl group. So there's my N. So here's my 5 carbon one, here's my 2 carbon one, here's my 3 carbon one. And then that ends up with a positive charge, and then that chlorine is a negative charge. And so this is what we call a quaternary ammonium salt. And so quaternary means 4, meaning it's nitrogen with 4 alkyl groups on it. And we said that whether they're alkyl groups or not, anytime nitrogen has 4 bonds, it has to form a salt, right? Meaning that because it uses that lone pair of electrons to form that new bond, that means that it actually has a positive charge. It's given away an electron, and that chlorine then kind of absconds with that extra electron, and we make our salt. So remember, nitrogen with anything less than 4 bonds is just an amine. Nitrogen with 4 bonds has to be that ionic salt. Yeah, there's no real way to show it. I mean, if we were talking about Na plus Cl, it's pretty easy to put them right next to each other, right? With something like this, anywhere you put that positive charge and anywhere you put that negative charge, as long as they're kind of close to each other, that's fine. I mean, if you put the plus charge up here, you know, or you put the plus charge somewhere else, wherever you put it, I'm going to be pretty happy with it. Okay, so that's one substitution reaction. The other one is actually from chapter 24, And it's, I don't know if it really has an official name. It's kind of a thionyl chloride reaction. And what we're really doing is we're activating the carboxylic acid to make it more reactive than it normally is. So if we take a carboxylic acid plus thionyl chloride, and we'll put down the formula for thionyl chloride in a second, then we're going to get what's called an acid halide plus HCl plus SO2 gas always. And so this is kind of like a combustion reaction in that we always get the same products, meaning there's always the HCl, there's always the SO2. This is another one of those reactions that's complicated. There's really 5 steps to it. And so what we're going to have to do is we're going to try to think about it as simply a substitution, and then technically it's a decomposition after that where the leftover products from the thionyl chloride automatically break apart into HCl and SO2 gas because it's more stable. But I got to be honest, sometimes you just have to brute force something if you don't want to memorize all 5 steps. And if someone wants, I can look up all 5 steps on the internet. I certainly don't have it memorized just because it seems excessive. So I've got a carboxylic acid plus thionyl chloride, which is SOCl2. And so the easiest way to recognize that this reaction is going on is if you glom onto the fact that SOCl2 is thionyl chloride, then you know it's a substitution. And what we're substituting is that OH group and a chlorine. And so I end up with a carboxylic acid halide. So acid halide, kind of like alkyl halide. The halide part is saying that I have a chlorine, bromine, fluorine, or iodine somewhere on the molecule. In this case, it replaces that oxygen group. And then I get the plus HCl plus SO2 gas. And if you think about it, what you really get when you have all of this laying around is that, you know, a whole bunch of SOClHO. And if you look at it, you know, that's just a decomposition reaction to form those compounds. And we could try to draw the Lewis structure and see why it happens, but it seems somewhat reasonable that we know that complex molecules can sometimes spontaneously decompose into smaller, more stable molecules, right? We had an entire series where we had carbonic acid, ammonium hydroxide, and sulfurous acid, in which we always broke it apart into water and either CO2 gas, ammonia gas, or sulfur dioxide like we have here. And so since those are small, stable molecules, it kind of makes sense. And again, that's just a substitution. You're just swapping, you're putting the chlorine there instead of the OH group. So there's 2 substitution reactions. And there's other reactions that you can kind of think about in terms of substitutions too, but they're usually better thought of in another method. So let's see, checking things off my list, I think we're down to the final reaction. And this reaction can be thought of in 2 steps or 1, and it takes what we did in the last step and it goes 1 step further. Basically, we take an acid halide plus 2 amines and we make an amide plus an amine salt. Let me go look real quick. It is sometimes called a where is it on my list even? Oh, it's just called an amide formation reaction. So it's just lumped under what they call formation reactions. And what formation reactions really are is they're simply one of the more common ways for making these type of compounds. So the way we make amides is by taking acid halides in reacting with amines instead of reacting, say, a carboxylic acid straight with the amine. It's also very similar to how we make amide bonds in proteins and amino acids. Well, yeah, amino acid chains, peptides. We'll worry about that when we get to that section. And you can either think about this reaction in terms of one single step, or you can think of this reaction in two separate steps. So let's take a look at it as one step. If I take an acid halide plus an amine, and I've got two of them, right? Oops, let's make them the same. I should also point out that obviously if you mixed up how many different types of amines you had and various things like that, you could get multiple products in a reaction like this. I will never do that, just because it's a uber pain in the ass. So the first step, what really occurs is that chlorine and one of the hydrogens swap places. So the first step is a double displacement or swap. And so what that results in is your amide, like that. And then what you really get is, for your second step, because you have HCl plus an amine, do you guys remember what we always said hydrochloric acid and amines make? They tend to make amine salts. And so in this case, what you're getting is an amine salt. So you're getting NH3 plus Cl minus. So you make your amide and you make an amine salt. And that's why you have to have two amines present. And what that really says is that once an amine sees hydrochloric acid, it immediately wants to react to form an ammonium salt. Because remember, what are amines really? They're kind of like carboxylic acids are acids. Amines are, say it, I can see it on your lip. They're bases, right? So one of the things we said is difficult or complicates matters sometimes in this carboxylic acid and then the amine chapter is that carboxylic acids act like acids. So depending upon the pH, they can either look like an acid and behave like an acid, or if I've got sodium around, they form the carboxylic acid salts, right? Same thing with amines. They can act like bases, and so if they see an acid around, or if there's a spare chlorine around generally, they're going to form an amine salt. And so what you get is, even though that first step automatically creates that HCl, that's that double displacement swap, but the second there's any HCl in the solution, another amine just says, oh, I'm going to gobble it up, or I'm going to instantly react with it to make that ammonium salt. And so even though it's two steps, it's not like you can just separate the steps and say, oh, we're going to just stop it after step one. That sounds like, something we'd want to do. And so you really have to have two amines present like that. And because this reaction is somewhat complicated and tricky, for instance, if I write the reaction with just just an acid halide and one amine, remember that looks a little funny, right? It's kind of like the primary alcohol dehydration reaction where they react with each other. So really it's a primary alcohol plus a primary alcohol, even though you write one. So if I remember right on the computer and in the homework, I always put that there's two amines there. So you know that it's this reaction right here. And it's that combination double displacement, a swap, and then again, anytime there's HCl present, make an amine salt.
Did that NH3 on the very last one come off of the NH3 the first one?
No, so we swapped, right, and then I have this HCl that was from the swap. So here, let me just show that first swap specifically. So if I react just the first amine, and I do a swap, then what I would get is my amide, and then I would get HCl. And see, then that HCl immediately reacts with a second amine, so we think about that as reacting with the second amine to make my salt. And so here's kind of step one, right? Oops, went too far. That's kind of your step one, and then your step two says take that leftover HCl and immediately react it with the amine, since that's what really happens. So what it says is that you have to always have twice as much amine as acid halide in this reaction. Otherwise, you'll only get half as much product, or you'll get a mixture of products. Now, I'm looking at my notes and I'm double checking things, and really I think that's it for reactions. And that means that that's mostly it for this chapter. There's some of those miscellaneous topics that I haven't talked about or skimmed over. I guess we can answer one of the homework questions real quick. You're going to get to it when we see it in the next chapter, but if I have this, what type of molecule is that? Yeah, if you're a chemist, it's a carboxylic acid. But we're going to learn that biologists, just to be annoying, or chemists, I don't know which way you could argue who's more annoying, but they like to have their own names. They're going to call this a fatty acid. So what is a fatty acid, but really just a gigantic carboxylic acid? So for instance, when we're doing the biology chapters, if you can start getting things like this into your head, that, oh wow, we're on the chapter on fats. Actually, what do we call that chapter? There's carbohydrates, oh, lipids, because it's technically considered a lipid too. It's a class of lipids. And if we can think about all of these things in terms of chemistry nomenclature, and just remember that every time we see the word fatty acid or fat, we kind of know what we're talking about because we've already had the chemistry section of it, then you'll find it's kind of easy to do those biology chapters. If everything you learn in the biology chapters is brand new and scary, then that's a lot more work. And so things like dehydration reactions, hydrolysis reactions, and making amide bonds, we're all going to see again, and a few of the other reactions here and there also. And so what ends up happening is the other part that it talks about is the formation of triacylglycerides, which is basically how we store fats. And so this is sometimes also called fat. Oops, there's an I in triacyl. Anyway, what that really is a reaction between, let me draw it all out just to be good. So this is a molecule we're going to be familiar with sooner or later. This is called glycerol. Glycerol is one of those molecules that crops up in your body quite often. And what happens is if we react a glycerol with a bunch of fatty acids, now notice I'm not being very specific here in that I'm not going to bother counting how many carbons I have because I don't care at this point. What I want you to focus on is what's happening. And they don't even have to be the same size. You can have them be longer or shorter. But we get a reaction like this where we subtract H2O, and now we start subtracting not one H2O, but oops, 3 H2Os. And so we end up getting a triacylglycerol or fat. This is how your body likes to store it. Very efficient, very easy to transport around. I should also point out that one of the things you're going to have to get used to also, and we'll worry about it in the biology chapter, is that these can be drawn about 100 different ways depending upon what you're focusing on. Meaning, notice that we even mixed line drawing and drawing the carbons out specifically, right? If I were to really draw this all line drawings, it kind of looks weird. It actually looks more like this. There's my 3 carbons, O, like this. And then one of them actually ends up facing the other direction due to geometry. We don't usually worry about that too much. Oops, I forgot to draw a little O in there. So I mean, you can see these molecules drawn in a variety of different ways. One of the things you'll notice is that on the test, I like to take and just randomly choose pictures from the internet that illustrate different ways to draw these. And so what you have to focus on is knowing what they are, what they're composed of, and then being able to translate in your head what that little picture means actually. They're usually 14 to 20 plus, with 18, 16, and 20 being the most common. We're going to have an entire chapter. I shouldn't say the whole chapter. We're going to have an entire section on things like this because we'll also talk about whether they have double bonds in them or not. You guys have heard of omega-3 and omega-6 fatty acids, and you've heard of cis and trans fatty acids. We'll talk about what all those words really mean. I thought it was funny when I first taught those chapters. I had no idea what a omega-3 fatty acid really meant, and then I read on it and I'm like, it's just where the double bond is? Wow. Omega-3 fatty acids sounds so complicated, but it's really where the double bond is. Same thing with cis and trans fatty acids. I was like, wow, trans fatty acids are bad for you, right? And then I'm like, well, shit, it's just cis and trans isomers. It's not even, you know, that hard to get a grasp on. What is hard is figuring out what is good for you and what is bad for you. And I think there's a huge component that is person dependent. I think there's so many factors that work into good health that what might be good for one person and bad for another. I mean, we can always point to the outliers like, you know, the 99-year-old lady that smokes and drinks beer all day long, right? Well, if you and I and the average person does that, we probably won't live to 99, but she did. So does that mean smoking's good for you and beer? I don't know. So, what other types of questions do you guys have?
Is this all stuff that's in the test?
Yes.
So are we going to review it all?
Tomorrow is a review day. Get all your homework done day, get caught up day, be absolutely positively ready for the test on Thursday day. Which means, and I had mentioned this over the weekend, you guys had a lot of work because you had to start studying for the test over the weekend, right? You're going to have potentially a lot of work tonight. I've got on the website all those extra little study guide sheets, right? So make sure you can start filling those in. But you guys know what to do now from the first two tests. A certain part of me says I shouldn't waste a day reviewing because you guys should have it down, right? But I do want to give everyone time to ask questions and things like that. But that means you have to do your part. If you come in and say, Jay, I have no idea where to start on reactions, I'll probably cover them, I will. But I'm going to look at you and be disappointed because you've now had 2 chapters worth of reactions to learn, to figure out a good way to study for it. And so, you know, I expect you to kind of come up with some themes. If you say, I have no idea how to do reactions, I'm going to look at you astounded because if nothing else, you should be able to pick out 1 or 2 that you've kind of mastered already, right? Like dehydrations. How many people feel pretty comfortable with those? Minus H2O. You know, how many people feel pretty comfortable with the whole oxidation schemes? You know, if you've kind of done your bit and studied hard for the first 2 tests and gotten down some of those basic things, then I would say 1/3 of the reactions in this chapter right now, in this last test, are things you've already had before and you shouldn't have to necessarily learn again. Or if you are learning it again, it should be, oh yeah, I just needed a real quick reminder for that. And then figure out some way to kind of do that. For the naming, same thing. What's the newest things for naming? What are things that we have to remember? What are unique about carboxylic acids, esters, amines, and amides? Well, yeah, you have to know the endings. Yeah, so esters have that weird space in them, right? Like ethyl, space, butanoate. I should point out, I graded some of you guys' homework. You got to work on the penmanship a little. Is that a space or not?
Yes.
Depends on who you are, right? Or is this supposed to be an underline or a space? I don't know. I got to be honest, if you're that sloppy on the test, I might be annoyed. Make sure that if you're using a line to indicate that space, like I mentioned, that it really is down at the bottom of the letters, not in the middle of the letters where a dash is sometimes. And if you're leaving spaces in words, then don't name something else like, say, N-dimethyl butanamide, because that sure looks like a space to me, right? Is there supposed to be a space there? No. So you've got to be consistent. If you're leaving lots of spaces randomly in words, then I'm going to take a point or two off here and there. If you're leaving out the dashes, you know, if you write 3,3-dimethyl dash pentanoic acid, well, there's supposed to be no dash there, right? And you do need a dash there, right? And so if you're just randomly putting in dashes and spaces and underlines and crap like that, and I can't tell what you're really trying to say, I am going to be a little picky on the penmanship, okay? So take extra care. If you literally want to put an arrow saying there's a space here, then that's going to leave no doubt in my mind, right? Whereas things like this, that's some doubts. Things like this, I mean, I probably think you get how to name those compounds, but by gosh, you're not really being a stickler for the details, are you? That's kind of like in math when these students seem to know what they're doing, yet somehow randomly minus signs just disappear halfway through a problem. Never been able to figure out where they go, but they disappear. Same thing here, your dashes seem like they disappear, they move around. Your brain's thinking too fast maybe and just skims and glosses right over it. So yeah, esters need a space. What else do we need to remember that's kind of different and unique? No, about anything. Of naming in particular is what we're on as a topic. What's special about carboxylic acids? Yeah, there's a space acid. So it's something oic acid. But most people kind of space that out properly. I would say the other thing is there's no location, right? And there's no location for those, right? Meaning those functional groups are always number one, so you don't have to tell me a number for them. What about amines? What's special about them? Right, so amines are just like this if we're have to have a picture associated with it. So what's special about amines? You need the location, right? That's something that, because the other three compounds don't need a location, a lot of people start getting sloppy and not putting the location in the functional groups. But that's fine for esters, carboxylic acids, and amides. They don't need locations because they're always number one. However, amines do need that location, so be aware of that. The other thing that applies to both of them is that whole using an N, right? And I noticed on a couple people, if you've got, say, some N-dimethyl, you need two N's. Just like numbers, you have to show every number. So if you have something like, you know, 3,4-trimethyl, one of those two things is wrong, right? And whether that means that you have to duplicate a number or something, whatever, or if you accidentally use tri instead of di, although that's less likely to happen, I think. But a lot of people forgot to throw in those extra numbers.
So how do you do the location for the N? Like if you have like 2 or 3 N's, how would you do the location for that?
What do you mean by 2 to 3 N's? There should only be one N in them.
Well, I know like
Oh.
in the homework when you're like doing the naming, like if you were given the name and you're trying to do the line structure, I thought it was really hard to know what carbon the N is going on.
Okay, so let's,
Does that make sense?
no, but maybe. Let's put it this way. So let's say I had, So you're saying you're not sure where to put the N on this molecule, right?
Right.
So all names, you technically start backwards. So first draw that hept, right? 1, 2, 3, 4, 5, 6, 7. And then notice that we need an amine, right? And we're working backwards, so where does the amine need to go? On the 3. Now notice, I don't know why, I started numbering backwards. What I always find funny is it's so annoying to grade homework, especially with these esters and amines and stuff, because some people will start counting from the left and some people start counting from the right. And so really there's kind of 2 answers for every question. So it's a little annoying. So there's the amine part, right? And then I've got 2-methyl, so I'll go put a methyl. And then that N-methyl and ethyl mean that it goes on the amine. Now, what I'm assuming you are having trouble with is figuring out where that amine attached to the main chain. And so that's running it backwards. Because I got to be honest, if you tried to name that from the front, you would go N, and you say, okay, I need an ethyl group, right? I need a methyl group, right? And then all of a sudden you've got that 2-methyl, and it's like, you haven't even drawn that part of the chain, so where the hell does it go? So remember, even though if you're really good, you can start from the beginning, kind of see the whole thing all at once, right? But really, we're naming everything backwards, or when we're drawing it, we sort of start from the butt instead of from the front. So, same thing with amides. I don't know why I said that. Maybe I was thinking, yeah, whatever. Oh, I guess we have to have a name. So like if I have something like this, again, I start from the back, 1, 2, 3, 4, 5, 6. Then I draw my amide group, right? Then I say, oh, I've got 2 ethyls on it. And so start backwards when you're drawing them, and that might help you figure out where the ends are. The other thing is if you do have more than one amine or amide functional group in a molecule, then we have to start calling them N and N prime, and guess what? We don't have those. We left those off. Yeah, see, that's a good question. Is that a space? No. That's just Jay taking a pause, not sure what he wanted to draw right next, and writing it. No, that's a perfectly valid point. Even I tend to be a little sloppy sometimes when I'm writing stuff, which is why if I really want there to be a space, you'll notice that even in class, I always underline that space to make it really obvious. And I always made it much larger than my dashes. I tried to make it thicker and at the bottom so that when I came to draw something like this, then I knew where everything went and I made the space obvious. At least I tried to, okay? I don't know, if you go back through all my lectures on tape, you might be able to find a case where I didn't, but I tried to. More questions? It can be on anything. We're kind of doing a lot of our review now.
Is there a specific reaction that you can tell the difference between
Yeah, we will probably, just because we're taking a lot of review days, skip the carboxylic acid amine lab, and that gives you, carboxylic acids, esters, amines, and amides lab. And that gives you several ways that you can differentiate between some of these compounds. So you could look in your lab book and kind of read those sections quick. Or what's probably the easiest way to differentiate, and no saying if you already know the answer and have asked this question, between a carboxylic acid and an ester? What's one of the, so say I've got a bottle like this, and I need to differentiate which one is which. Oops. I don't know why I drew the carbon on that one, but I didn't on the other one, whatever. How could I differentiate between those two compounds? What are some fundamental differences between carboxylic acids and esters? Okay, so that's probably the key, so focus there. How can I test if there's an OH group there versus not? What? Yeah, I said if you already know the answer because you asked me this question to shut the hell up. Oops.
Well, they don't.
Now, they probably have no idea what the dip means anyway. So how about this? Acid, carboxylic. That took him like 5 times too, apparently. So what's special about acids? Yeah, I know. That's why I'm saying skipping the lab is a little sucky on that part. So acids, remember, can measure pH, or you can use litmus paper. So the dip, apparently. Yeah, I know, because you're supposed to take a dip. No, you're not supposed to. Exactly. Proper chemistry technique is to dip a glass stirring rod in there and take out 1 drop and test it, not to stick the pH paper in there. So, yeah, one of the biggest differences between carboxylic acids and esters is simply one is an acid and one is neutral, because it doesn't have that hydrogen that can be lost. What if I wanted to differentiate between a carboxylic acid and an amine? Same thing, one's an acid, one's a base. What if I wanted to do amides and amines? A little bit less so. You have to be a little careful. An amine is going to be a much stronger base than an amide.
So your paper change colors better?
Yes. Or it'd be a little harder to tell an amine from an amide, but mostly you would be able to do a pH. Worst case scenario, if you don't have pH paper, almost every chemistry lab has a pH meter that you can stick in it. So that's probably the easiest way I can think of to differentiate between a carboxylic acid and an ester. The other way you could try to do it is if you did a hydrolysis reaction, then maybe you could realize that then you could have your ester would be a combination of a carboxylic acid and an alcohol at that point, right? And then you could try to separate those in some manner, but I don't think it's going to be very easy. You could try, because like I guess if you took both of them, did a hydrolysis reaction on it, and then oxidized it, you'd be able to tell that you had an alcohol, because alcohols are oxidizable, whereas carboxylic acids are not. But I would say sticking a piece of pH paper in there is probably the easiest. The other way would be simply to take a whiff. Acids usually have a sharp odor to them, whereas esters will not. And I think that's mentioned in your book also. Esters tend to smell good. Maybe we should pull that lab. Jess, wake up. Maybe we should pull that lab out and give it a go, because that's one of those labs where everything smells good in the lab.
You said that less than 10 carbons are stinky, and if they're greater than 10,
Right, so that's not the best way to do it, but if it was a rather large one, you could tell by smell. Other questions, or are you guys just going to giggle over there? I don't know. She's not very good in a fight, from what I understand. No, because I'm going to lose either way, Jess. If I do beat you up, I beat up a girl and a student. And if I get my ass beat up, I got beat up by a girl. So it's a no-win scenario for me. I cannot possibly win that battle. Now, if we did what we used to do in Student Senate, which is